Hi, Deborah.
Hello.
How are you today?
I'm doing all right. How are you?
Fine. Made it to another Friday. I'm marking.
Yeah.
It's getting close. Let's see. Tiara's trying to get in here. Why do I have trouble getting in? All right, come on. A burrito for lunch. I guess that's what that looks like. I'm gonna wait till after class to eat. Come on, Tiara. Not working. Hmm. She's on her way, maybe. Yeah, there we go. You got in finally, Tiara. She's not listening. You still got her mic off. I can't see anything but the top of her head. There you are. I thought you were sleeping.
No, I'm reading this source, trying to find something for my presentation.
What time's your presentation?
Oh, it's due today.
What's it for? A presentation for what?
Genetics.
Genetics. Is that what y'all are doing for a final exam?
No, this is for lab.
Oh, okay. All right. So it's late. It's right after class, or today, or later today.
No, it just has to be turned in by today.
Oh, okay. All right. Okay, let's see. There's Deanna. I get her in. Okay. I don't know about Tiara today. We'll see. She hadn't emailed me, so I guess she's coming. There's Dion. Okay. Randolph Macon. What you wearing that Randolph Macon shirt for?
My brother gave it to me.
All right. That's okay. Brother gave it to you. I can't argue with it. Did he go to Randolph Macon? Did he go to Randolph Macon to college, Dion?
That's where he's at now.
Oh, he's there now. Okay. My very good friend that I used to teach with at Salem, who was in the economics department, went to Randolph Macon. She left a long time ago, but good friend. Guys, a couple of things. I sent out that email last night because I honestly could not remember when you guys were supposed to get the Power Series thing in. When was it, by the way? Today sometime? Because I got Tiara's, I think, because I hadn't looked. But you know what I'm talking about? The Power Series one? Okay. So when did I say? Today? Saturday?
I
Okay.
think you said by Saturday morning.
Okay.
Yeah,
Saturday
you
morning.
did say Saturday.
Okay, that's fine. It's the one with it's got 4 problems on it, and you'll see what it is on the. I haven't assigned any other quiz. Well, there's another quiz on Power Series representations, I think. I'll look at that. But this is the one that's due. It's just using the ratio test. Don't forget, when you hand it in, you're trying to find an interval of convergence. So you find out where it converges, and then you check the endpoints. So there's not enough room on the paper to do that. Okay, so you might want to write it on a different sheet of paper. I tried writing it on the one I wrote it on, and I don't know why I gave you so little room, just because I could get it all on one page, I guess, but it just didn't. It's definitely not enough room. Okay. So questions, anybody today?
I hope I did it right.
Okay. All right. I'll look at it. These are all sort of like test runs for the case runs for the next test is basically pretty much going to have just series stuff on it. I'm going to do something else next week with polar coordinates, which has nothing to do with series. I can tell your neck's still hurting because you got something.
My neck still hurt. Like yesterday, I could not. Like literally, I was crying.
Did you just sleep on it wrong or something? Or
It was that
Got bad audio connection. Okay.
No, my sister, as soon as she came in this room, as soon as my sister came in the room, my neck started hurting. I'm
Okay.
blaming her.
Oh, that might be a coincidence. You might not want to blame her for very long, but anyway. So guys, I don't want to talk to Siri. Why is that on there? So that'll probably be towards the end of next week. After this, we got one full week, and then we got Monday, Tuesday, Wednesday. I really don't want to do anything much Monday, Tuesday, Wednesday, except kind of wrap up what I've done next week. I'm going to talk to you about your final exam. Typically in this class, always in this class, I can't remember when I have never done it, I give a comprehensive final. What I'm going to do this time, which is sort of different, is we're going to do this last test on series and maybe do a little bit more on these polar coordinates. I'm going to calculate your grade after that with your daily grade and the tests that you've taken and everything. And if you're happy with your grade, I'm not going to make you take a comprehensive final. If you are not happy with your grade, you can't, or even if you're happy with it and you just want to have some more happiness by taking a math final or whatever, you can take it. And if you do better on it than your lowest test grade, I'll put it in the place of your lowest test grade. Now, whether you think that's worth the effort of, you guys don't have too many low test grades. I mean, there might be one, and everybody might have one that's lower than some of the other ones, but I'll give you I'll give you your average, and I'll let you decide. And it doesn't have to be an A. It can be a B, okay? And I think everybody in this class got A's and B's, so I'm not worried about that. And that might take some pressure off of you with other courses, whatever. And I don't think it'll hurt you in the long run. We've had a test on everything. So that's my plan. It's not what I advertised initially, but does anybody have any serious objections to that? Is that? No, I saw Alexis starting to smile. I couldn't quite tell about everybody else, and Tara looks like that. Whatever she's getting ready to present is giving her a big headache. But anyway, yeah, I can tell. So what? You got a question? Okay. Yeah.
Well, I guess when we get to it, but I watched your little video on YouTube.
Yeah.
Can you go over that last example? Because you were zooming, and I didn't understand anything.
Yeah, you mean the examples where we made power series representations for things?
It was the very last example.
Okay.
I think it's the one that includes the log.
Okay.
Yeah, the EX thing.
Okay. All right. Good. That's a good place to start. So let me go ahead and share the screen, and we'll do that. Okay.
These due dates. I'm confused on what's due, what's not due.
All right. I'll tell you what's due tomorrow.
Saturday, Sunday, then you said Monday.
I'll tell you what's due tomorrow. What's due tomorrow is it's online, and it says ratio test power series. It's you click on it. It's got 4 problems on it, and it says tell me what the interval of convergence is, and I'm telling you to be sure to check the endpoints. It's the stuff we were doing yesterday. Well, earlier, before I got to the new material yesterday. Okay.
And that's due tomorrow.
That's due tomorrow. Just get it to me tomorrow sometime, guys. That way I'll have a little time over the weekend to grade it. I'm trying to get things back quickly because I want us to be ready to take the test when the end of the week comes, okay? All right. Sharing is paused. Why is that? I don't know. We'll wait for it to come up. Doesn't come up, I'm going to have to log back on. Try this. Come on. Come on. That's what I was going to do. All right, there it is. Okay, let me go back to what I was doing yesterday and talk to you about how we get power series representations for functions. Let's see if I can find it. Let's see. I read all of this stuff here. That's the homework key. Oh, by the way, the homework key for this, the power series representations, that the homework that I gave you, that those 5 things to write in terms of a series by seeing it as a geometric series, is right there. It's on Moodle. Okay, so you might want to check that when you get to do that. You might have already checked it. Shoot, where is it? I don't think it's this one. No, it's not that one either. None. 2, 3, 4, 5, 6, 7. I can't find it. I know it's on here. So much stuff. That it's 10. All right, I'll just start with I'll see if I can find, let me see if I can find the lecture, and then let me go to the one I was going to do, and then I'll add some pages at the end, and we'll look at the homework.
Happy 1st of May, y'all.
Happy May Day, whatever that word. There you go. All right. So this is the thing I was going to do today, but I'm going to hold on. I'm going to hold on to that for a minute and see if I can try to figure out what the examples that we were talking about here. Oh, let's see. Maybe I'll just look at what I got here. Let's go this way. Okay. So I think that what you're talking about is how we got some series that we've got. And we were in 11.8. And that was right. Nope, we were in 11.7. And one thing we said was that if we want a power series representation of a function, we could see it as a geometric series. And we could write it as a over 1 minus r. That's all that practice I gave you on that homework. We could also get a power series representation by knowing another power series representation. So for example, e to the x was the sum from x equals 0 to infinity of x to the n over n factorial. And if you write things out like that, it was 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. There was another, and then so on. If we wanted to, we could use that one to find x e to the x. If you wanted to find x e to the x, all you have to do is take e to the x and multiply everything in here by x. If you wanted to find e to the x squared, since we already know that one, you could put in an x squared everywhere there's an x. So it's e to the x. Now I want to find e to the x squared. I'm going to just put in an x squared there. So x squared over 2 factorial, and this next will be x squared cubed over 2 factorial, and so on, 3 factorial. So on. So we could build these things based on whether it was a geometric series or whether we already knew one. The one that I think you're probably talking about is this one. If we could say, let's find a series representation for the log of 1 plus x. Yeah. Is that what you're talking about, Alexis?
Yeah.
Okay.
I was just confused. Like, when do we know to take the integral?
Well, here's the thing. Here, we're going to know more than this after today. But here's the thing with this. If we know a derivative or an integral that looks like a geometric series, then since we can integrate and differentiate these power series, we might be able to get a representation for it. So for example, if I say to you the derivative of log of 1 plus x, what would you tell me the derivative of log of 1 plus x was equal to? Just that, not series or anything. What is it equal to?
X.
Okay, how do you take the derivative?
No, I got it.
Okay.
It's 1 over.
Yeah, you got that.
1 plus x.
Exactly. Okay, got it? Everybody do that? All right. Okay. Had a little brain fart there. That's okay. So what happens here, guys, is this. If I know the derivative of that looks like that, well, you know what? That looks like a geometric series. So I might look at that and I say, well, you know what? I could write that one as a geometric series where it looked like that. And what would my A be?
1
1. And my R would be what?
minus
Negative.
x.
Minus x. So this thing's going to converge for the absolute value of minus x, or x less than 1. So x between 1 and minus 1. Okay, that's where it's going to converge. And it'll look like this, the sum. The A is 1. R is minus x to the nth power. So from n equals 0 to infinity. If I wrote out some terms of that, I'm running out of paper here though. If I wrote out some terms of that, it would look like this, guys. The first term, if I let it, n be 0, anything to the 0 power is going to be 1, so it'll be 1. If I let n be 1, it'll be minus x. If I let n be 2, it'll be plus x squared. If I let n be 3, it'll be minus x cubed, and so on. So you're okay on that, on writing that one out like that?
Yeah.
So here's the deal. What you know is that the derivative of the log of 1 plus x is that thing, and it looks like that. So that's easy. Now I got to hold on it here, because if I know the derivative of that looks like that, what will I do to undo this derivative over here?
The integral.
Yeah, let's take the integral. And if what I do on one side, I got to do on the other, okay? You good with that? I mean, so what's the integral of the derivative? It's going to be log of 1 plus x.
I ain't heard it.
All right, I knew that this was equal to that, and what I was looking for was just that thing. So I'm going to integrate both sides to undo that derivative. And if I integrate the left side, I got to integrate the right side. So what happens here is what we learned yesterday was that if you have a power series representation, you can integrate it a piece at a time. So what's the integral of 1?
X.
It's x. What's the integral of x?
Negative
Negative what?
x squared over 2.
Yep. And the integral of x squared?
Long range. Okay.
X to the third
I
over
know
3.
Okay.
x cubed over 3.
Over 3. Okay, we got the idea here. But now, see what you found here? You have found, by knowing that the derivative of that thing looked like something and knowing you could integrate both sides, you found a series representation for log of 1 plus x. That's
So
all it is.
do we always, when we do this, we have to do the derivative in the integral?
Depending on what you've got. Sometimes you might know the integral of something and you can find the derivative or whatever. But the point here, guys, is up to this point, we have to somehow link it to something about a geometric series, because that's the one we know how to do. The only one we've done that wasn't linked to a geometric series so far was e to the x. And we did that by getting a series representation and taking its derivative and showing that it was exactly the same. So we knew a function whose derivative was the same. It was e to the x. So that's the only one we got. All these other ones are linked in some way to a geometric series. And this one was linked to it like this. We don't know how to do the log of 1 plus x. We do, however, know that the log of 1 plus x is something that looks like a geometric series. So if I can figure out what that series is, I can integrate both sides and get the one that I was ultimately after. Okay. Now that, guys, doing that is really too heavily dependent on making some kind of connection between a geometric series. Today, I'm going to show you that we don't have to do that. All right, there's a generic way to write these things that's not dependent on geometric series. Although if you could make it look like a geometric series or some piece of it, like the derivative or the integral looks like a geometric series, you should go down that road because it's going to be easier.
So are geometric series like what people usually want to do?
No, because you can't do, there's some functions you can't, well, if it is a geometric series, you want to do it like this because it's easier. But if a lot of times what you have are functions that you don't see, you can't see as geometric series. So suppose, for example, I said, let's write a series representation for sine x. Well, the derivative of sine x is cosine x. The antiderivative of sine x is minus cosine x. You don't know any kind of connection to this function to a geometric series. You just don't. So the question is, how do we do something that you cannot make that connection with? If you can make that connection, make it. If you can't make the connection, we got to have another way to do this. So that's really what I'm going to be after today.
Can you see me?
No, I'm looking at I'm still looking at the top of I'm looking at the top of Dion's head. Now I can see. I can't see you. You're black now. I mean,
I don't know.
you're in a black
I
screen.
I don't know what to do because
Okay, sorry.
it just keeps doing the same thing. Like,
I can hear you. It's okay.
Oh,
Can you see my screen?
I can see everybody, but I can't see my face, and I don't like that because I know I'll be looking crazy.
Well, that would it be better than if you didn't see your face? I mean,
No,
I'd be happy if mine blacked out. Okay.
I can fix how I be looking, not
Alright.
looking all confused.
All right. So if you just since I can't see your face and I can't see your hand being raised, just break in if you got a question. Okay. But the point is here, guys. Number one, if you can see it as a geometric series or a derivative or integral, then you can do it by geometric series. If you see something like this, you got a problem. We don't know how to connect that. So here's the thing. Today, I want to talk to you about a generic way to find power series. Okay? All right, it's coming into focus. And it's the last thing we're going to do with series. I don't know if I finish it today or not, but I'll finish it on Monday if I don't. There's, so what I wrote in the introduction is exactly what you were asking me and what I was trying to say. It says, we've seen how we can write a series representation of function if there's special types it can fit into. A geometric series, a derivative or an integral of a geometric series, or maybe something like e to the x where we just said, here it is, it's the thing that its own derivative. Well, what are we going to do if we have some function that doesn't really have any connection to a geometric series? And my examples typically, at least when I begin this lecture, are how are we going to do this for sine x and cosine x? It doesn't have derivatives or integrals or anything else that has anything to do with a geometric series or putting it in that form. So here's the first question. First question is, if there is a power series right here that looks like that or that, what does AN look like? In other words, what does the coefficient on your x to the n? Now remember, this is a power series that's centered at 0. This is a power series that's centered at c. So for example, if I said e to the x is x to the n over n factorial, the an part of that, is 1 over n factorial. That's what an is there. And of course, you know, if it's centered at 0, we're just going to have powers of x to the n. If we had this one we just talked about, this log of x plus 1 looked like this. If I found a pattern for it, it looked like that. This is powers of, this is about 0. I started it at 0, and the pattern meant I had to add 1 onto it, but that's okay. But the an part, guys, is this part right here, the coefficient on the x part. That's the an. If we could figure out what the an looked like, we'd have a power series representation for it. Okay, so that's what I'm going to try to do. I'm going to see if I can figure out how to do that. My question two is going to be a little bit beyond our grasp here, but it says, does a power series representation always exist like this? Can we always find a power series representation for any function? Not necessarily, but we're only going to work with ones where we can. Okay, so you can, there's certain conditions on this, which are covered in the book, but I don't think we need to get into that right now. So I'm going to focus on question 1. If we have a representation, if I write it out generically, if I let it n be 0, it's a0 x to the 0, which is a0, a0. If I put in 1, I'll get an x to the 1. If I put in 2, I'll get a2x squared, a3x cubed, a4x to the 4th, a5x to the 5th. You get the idea. Those would be what all the terms look like. The question is, can I find out what these A's look like? If I can find out what these A's look like, and ultimately the generic one, AN, then I can tell you what the power series is, if I know what that looks like. And there's a pretty sneaky way to get it. And I'm going to use this. Let's keep an eye on this thing right here. I kind of wrote out a bunch of terms for it right there. Okay. So here's the function I'm trying to represent there. And I'm going to say a couple of things. I am first going to note right here, if I said, according to this series, what would f of 0 be? Now, if that's f of x, and I plug 0 into this whole series representation, what would f of 0 be? Now, I'm plugging it in for x, guys. What would be left here? If I plug, anybody?
0.
0. Well, I get zeros everywhere there was an x, definitely. But there's one place where there isn't an x. Where's the one
A of
place? Where,
0?
yeah,
sub
A0. So if I plug 0 in, whatever this representation is, I should get A0. Okay, here's the next thing I'm going to do. I am going to take the derivative of this thing. When I take the derivative of A0, that's just a constant, so it's 0. The derivative of A1x is A1. The derivative of A2x squared, and guys, these are just constants, so that's going to be 2A2x. So that'll be 2A2x. The derivative of the next one will be 3A3x squared. The next one will be 4A4x cubed. And you kind of get the idea here. I'm just taking them. The next one, the last one I wrote, there's a bunch more out here, but I'm trying to look for a pattern. This will be 5a to the 5th x to the 4th. So if that's the first derivative of the function I'm looking for, what should f of 0 be if I plug 0 into that one?
A sub 1.
A1, exactly. That's the only thing that's left there. So if I plug in 0 to the function itself, I get A0. If I plug in 0 to the first derivative, I get A1. All right, I'm just going to continue doing this. Look at this thing again. Let's take the second derivative. Now, guys, you can take the second derivative from the first derivative. So let's just look at the first derivative. The derivative of A1 is 0. What's the derivative of 2A2x?
You know.
I know, but do you? The derivative of 2A2x.
Yeah. I can't think.
Well, what's the derivative of 5x?
5,
What's the derivative of 10x?
10,
10. What's the derivative of 2A2x? These are just constants, guys.
2.
2A2. That's just a constant there. Okay, look carefully here.
Why
Right.
can't we put it like that?
Derivative, that 2A2 is just a constant. So you bring the 1 down, you're going to get 2A2. What's the derivative? Then tell me what the derivative of 3A3x squared will be.
6A3.
6A3. But you know what? I'm looking for a pattern. So I'm gonna write that as 3 times 2 before. I'm not gonna multiply it out because I really want to see some kind of pattern here. So that's 3 times 2, A3. Did somebody here must have gotten bounced out, or maybe she came back in. Okay. If you look at the next one, it's going to be 4 times 3, A4, x squared. Look at the next one, it'll be 5 times 4, x cubed, and with the A5 down there. So there's the second derivative right there, just looking at that one. Now, what happens if I plug 0 into the second, there's the second derivative. What happens, and there's the third derivative that we just got. We got the second derivative, third derivative from the second derivative. What's f of 0 if I plug 0 into the third derivative? What's left?
3 times 2a sub 2.
3 times 2a3, because everything else has got an x in it. So there's that one. Okay, let me highlight these in a different color for a second, guys, because I'm looking for a pattern. I knew that f of 0 was A0. I knew that f prime of 0 was A1. I found out that f double prime of 0 was 2A2. I found out that f triple prime of 0 was 3 times 2A3. Let me see if you can predict the next one, because then I think you can see the pattern. If I said the fourth derivative without doing the derivative, can you see what the pattern is here? Let's see, let's look at it. When I had F1, I had A1. when I had F2, at the second derivative, I had 2 times A2. When I had F3, I had 3 times 2 times A3. What do you think F4 is going to be?
4 times 2 times, I mean, 4 times, you know, counting down.
Yeah, count down. I don't think you're going to count down all the way, but I think it's 4 times 3 times A4.
Yeah.
So look at it, guys. This one counted at, I mean, you'd have to see that a little, well, I mean, well, it does count down, all right? It does count down. So but it counts down to, that's 2 times 1. It counts down to 1 less than the derivative. Okay, look at that. This one counted down to 2. That was 1 less than the third derivative. The fourth derivative counted down to 1 less. It counted down to 3. Okay, so that's what I'm thinking the pattern is. Again, we'll do one more. Let's see. If I had what did I have? F3, I had F4. If we go by the pattern I'm talking about, F5 of 0, it's going to start with a 5. It's going to count down to 1 less than the derivative. That's a 5. That's Roman numeral 5. And then notice the subscript on the A is going to be the same as the derivative. So that was going to be A5. You could play it out with the derivatives, but that's what's going to happen, guys. So here's what we've got. I think that the AN is going to look like this. If I have the kth derivative, that's a K. If I have the kth derivative, we said it was going to count down to 1. Whoops, hang on, I got an error in here. That's -1 right there, okay? I said it was going to count down to 1 less than the derivative. So it starts at N, or it starts at K, counts down times 1 until you get down to 1 less than the derivative, okay? And then this power right here is going to be the same as the power of the, the same as the power as the x5. This is going to be the N. I should have an N here, guys. I'm sorry, I'm messing up the pattern here. If I want to say Fn of x, it's going to start counting down with N. For instance, if I had the third derivative here, it was 3 times 2. I'm going to start counting here, N times N minus 1, until I get to be 1 more than that, or 1 less. So it'll be N minus K. And then this thing right here ends up being N minus K. All right. Let me show you what's happened here on the next page. I'm getting a little bit messy here.
Wait, does that say F of K? Wait.
F sub K. It said F sub K. What I mean by that is the kth derivative. But
Okay.
down here it says N, the nth derivative. But
Okay.
let me clear it up a little bit. Let me clear it up a little bit, guys. This will look better. F of 0 was A0. F prime of 0 was A1. F double prime was 2 times 1 times A2. F triple prime was 3, 2 times 1, A3. Of course, that 1 really doesn't make a difference there. F4 was 4, 3, 2, and then 1, A4. F5, you know what F5 is going to be. When I plug in 0, it'll be 5, 4, 3, 2, 1, A5. So what does this look like to you guys? What does that look like?
Factorial.
It looks like that factorial stuff, doesn't it? So in other words, in this one, this F2 was 2 factorial times A2. F3 was 3 factorial times A3. F4 was 4 factorial times A4, and so on. You've got a pattern now. 5 factorial times A5. So if you look at the nth derivative, it's equal to n factorial. Notice that. So I'm counting down from n down to 3, 2, 1. So this is n factorial times an. Now, what that says is if I solve for an, which is really what I'm looking for, It's the nth derivative at 0 divided by n factorial. That's the pattern we saw. The nth derivative at 0. That's not nth power, guys. That's nth derivative over n factorial is what all the ANs look like. You can find A1 like that. You can find A0 like that, and so forth. Now, we've got the pattern, but I want to show you how it actually works with a function. But this has a name. The name of this, of what we're getting ready to do, is something called the Maclaurin series. Now, a Maclaurin series is this. If a function has a power series representation, sum from n equals 0 to infinity of an x to the n, with a radius of convergence r greater than 0, we got powers about 0, powers of x about 0. Then f sub k exists for every positive integer k. Now, all that means is no matter what the positive integer is, that derivative exists. The 15th derivative exists. The 20th derivative exists. That means you can get as many of these terms as you want. And the an always looks like this. That thing we just found.
So that man discovered it?
Yeah, and that man was named Colin Maclaurin. He was from Edinburgh, and he was the head of the University of Edinburgh's math department, and he was appointed or recommended for that position by Isaac Newton. So he was, which was a big deal.
Old.
That was a big deal. And
He's-
people,
I did not know he was that old.
yeah, he's pretty
He
old.
dead.
That was in the early 1700s, guys, early 1700s. And
I've never heard of that school in my whole life.
no, well, it was a big school in Europe at the time, and it was in 1725 before we even had any universities. Well, maybe Harvard, but that was about it. Okay, so lots of people go to the cemetery where he's buried, but they don't go to see his grave. Okay, I did. I went there to see where he was buried, but I did go for the other reason. And here's the other reason: was in the early in the I think it was in the 1800s. There was a man that belonged to the church where he's buried in the yard. There's a man that belonged to the church, and when he died, he had a dog that would not leave his gravesite. He laid on top of his grave, and people fed him until he died. The dog lived for years. The dog, yeah. When that guy died, his dog laid on his grave. Okay, all those years. And the dog's name was Bobby. And there's a statue in Edinburgh dedicated to this dog. And this same graveyard is where that guy was buried, where that dog lay. Okay, so that's why people go to that graveyard. They don't usually go see Maclaurin's grave. They do go see this guy's grave where they called the dog Blackfriars Bobby. Okay, so anyway, there's your little math history lesson for the day. All right,
Yeah,
let me show you
teach
how.
that class.
What's that?
You should teach that class. I'll take it.
Okay, it's a fun class because people don't really pay much attention. A lot of people don't pay any attention to the history of math, and it's got a lot of neat stuff in it. All right, let me show you what I lost it. Let me show you what we found out here. Here's what we found out. I know, guys, that what we did was we found a series representation for e to the x. We knew what it was. I'm going to show you a different way to find that. We knew it because we found something so when we differentiated it, we got the same thing back. But what we can do is this. Suppose I want a series representation for e to the x. And I don't know the sum from n equals 0 to infinity of a0 plus a 1x plus a 2x squared plus a 3x cubed, and so on. And I don't know what a0, a1, a2, and a3 are. This formula right here, this f of 0 over n factorial, what I just found out was that these coefficients look like this. An is the nth derivative evaluated at 0 over n factorial. I can find any one of them by doing that. Now here's what it takes. It takes the derivatives. I need to find the derivatives of the function. So tell me what the derivatives of e to the x are.
Easy.
They're always e to the x, aren't they?
Yeah.
So here's the thing. Then a0 is and 0 here means the function itself, is e to the 0 over 0 factorial, which is 1. That tells me that that is 1. Now, if I take the first derivative, I know the first derivative is also e to the x. So if I say a1 is f prime of 0 over 1 factorial. But if I plug 0 into the first derivative, still e to the x will be e to the 0 over 1. So I know that this coefficient right here is 1. All right, let's go to the second derivative. That'll give me my a2. The second derivative is e to the x. Plug in 0, I get 1 over 2 factorial. See, I'm dividing it by 2 factorial because that's what we just proved. It looks like that. So that one would look like 1 over 2 factorial. 1 over 2 factorial. These are the coefficients there. Look at another one. Look at F3. Or A, let's see, that's A0. We had A0 was 1. This was 1. This one right here was 1 over 2 factorial. A3, so look at A3, the third derivative is e to the x. If I plug in 0, I get e to the 0 over 3 factorial. That's 1 over 3 factorial. That's the one that goes with that one. So what I've got in the end is that this looks like 1 plus 1x. 1 plus 1x plus x squared over 2 factorial plus x cubed over 3 factorial and so on. Then that's what we found that it was before. It was 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And if you differentiate that, you'll get the same thing back. But this was a way to find the coefficients. Now, here's what I want. This one's almost too easy because all its derivatives are the same. So what I want to do is I want to find the power series representation for sine x. It's called Maclaurin series when you're going around 0. All right, so let me show you what I want to do. That's what I said. Remember what E looked like? Hey, it looked like that, and I just generated all those coefficients. 1 over 2 factorial, 1 over 3 factorial by looking at that thing that I had up here. All right, again, guys, AN, what I'm going to be using is I can find these ANs by looking at the nth derivative at 0 over n factorial. Now, f prime of 0, or the nth derivative in e to the x was easy because it was always e to the x, and e to the 0 is 1. All right, let's look at this one. Okay, so here's my job. My job here is to take sine x and figure out what the coefficients are going to be on the power series. And here's the power series generically written out, guys. I want to find A0, A1, A2, A3, A4. Okay, so I need some derivatives. There's the function. I need some derivatives. Because remember, I'm going to plug in 0 to all those derivatives. They're not the same anymore. They're not as nice as e to the x, but this is going to work. If I take the derivative of sine, it's cosine. If I plug 0 into that, cosine of 0 is 1. So what that says here, a couple of things. Well, let's start with f of 0. We know that a0 is going to be f of 0 over 0 factorial. Well, the function was the sine. What's the sine of 0, guys? What's the sine of 0? 0. Okay. So, guys, I'm going to go, and we can just barely see it here. Let me see if I can get a little further up. There we go. A0 is 0 here, because that's what I got when I plug 0 into that function and put it over 0 factorial. Let's find the next one. What's the derivative of sine x? Cosine x. If I evaluate that at 0, I get 1. So A1 is 1 over 1 factorial. So what's 1 over 1 factorial? That's the one I'm going to put on x. All right, A1 is the one I put on x to the first. All right, let's look at the next one. All right, guys, I'm going to try. I'm running forward. I should have left more space here. But let's do the 2. What do I get if I plug 0 into minus sign?
0.
0. So that's 0 over 2 factorial. Look what I got right here. That's 0 over 2 factorial, which is actually 0. I'll worry about the fact that it drops out in a minute. If I go to the third derivative, I'll just write it here. A3 is going to be f triple prime of 0 over 3 factorial. All right, what's f triple prime of 0 here, guys? What happens when I plug 0 into the third derivative of cosine?
-1.
I get -1, because cosine 0 is 1, I get -1. So that's going to be -1 over 3 factorial. That's what I put right there, -1 over 3 factorial. There's a 1 there. Okay. Go to the fourth derivative. There's a -1 in there, guys, hard to see. The fourth derivative is sine x. If I plug in 0 to the fourth derivative, that's going to be 0 over 4 factorial. That's what I got right there. I'm figuring out the coefficients. I'm going to do one more. F to the fifth. That's not the fifth. It's the fifth derivative. And the fifth derivative is cosine. Plug in 0 to cosine, you get 1. So that coefficient is going to be 1 over 5 factorial. What do you think the next coefficient is going to be, guys? Look at the sixth derivative. What's the sixth derivative going to be? If when I plug in 0 to that, I get 0. It'll be 0 over 6 factorial, right? 0 over 6 factorial. Now, here's what I found out. I am putting, these are the ANs that need to go on that. That drops out. The ones with the zeros drop out. Okay. The ones with the zeros drop out. So that one's gone. That one's gone. That one's gone. What I have left is x over 1 from that one. This one I have minus x cubed over 3 factorial. That one's gone. The next one was plus 1 over 5 factorial. I was going to ask you to guess the next one, but I wrote it in there. The next one would have been a sine, the sixth derivative, but the sine of 0 is 0, so that one's going to be 0. But if I look at the seventh one here, the cosine of 0 is -1, so that's going to be -1 over 7 factorial. There's a pattern there. Okay. Do you see the pattern, guys? What do you think about the powers on x? What kind of pattern are you seeing? They're odd. All the ones with even ones are 0 because all the ones that had even derivatives were sines, and sines are 0 at 0. Tell me what you think the next one's going to be.
9.
Do you think it's going to be plus or minus?
Plus.
Plus.
Okay, it's going to be plus. Good. It's going to be plus because what I've got right there, I've got alternating things here. So the next one's going to be x to the 9th, 1 over 9 factorial. Now, I want to show you, I'll give you a generic term in just a second, but I want to show you something. I want to prove to you, well, I want to convince you that this works. So what I'm saying is, that is a series representation for sine x. Now, what it says basically is I can use it to compute sine x if I need to, but let's just do it. If I say to you, I want you to use your calculator to find the sine of 0.2, and you got to put your calculator in radians here, guys. Sine of 0.2. If I put that in the calculator, I get 0.19866933308. So you want to check it, get your calculator out, get it in the radians, put in 0.2. Now 0.2 is close to 0. That means that this series is good close to 0 because I'm evaluating it at c equals 0. It's centered at 0. So now let's do it with the series. There's the series. If I plug in 0.2 everywhere there's an x, you can check me on this, guys. I didn't do the 9th term. I just did these right here. That's 0.2 minus 0.2 cubed over 6 5 factorial is 120, so I just went ahead and did that. 0.2 to the 5th. 7 factorial is 5,040, so that's 0.2 to the 7th. When I computed that on the calculator, I got 0.198669330. It is good to that many decimal places, and that's as many as my calculator would give me. All right, so I've got a polynomial that allows me to figure out what the value of sine is. Okay, so it's pretty good. It's good to all those decimal places. So one more thing, and then I'll let you go. I want you to remember here a couple of things now. Suppose I said, I want to find the power series representation. Oh, by the way, here's the generic term. 2n plus 1 is the way we generically say it's odd. It's the odd number factorial down here, and it's alternating, so I put a minus 1 to the nth in it. So 2n plus 1, 2n plus 1. I'll get you to do one more thing on that in a second. I don't really have to go through all that work for cosine if I don't want to, because, you know, now I know sine. How are sine and cosine connected in calculus? They're derivatives. The derivative of sine is cosine. You know what? If I want a power series for cosine, all I have to do is take the derivative of this thing. So I'm going to do that. What's the derivative of x? 1. I'm going to do it, and then I'm going to, this one will be minus 3x squared over 3 factorial. This one will be 5x to the 4th over 5 factorial. This one will be, this is a 7th power, so 7x to the 6th over 7 factorial, and so on. Tell me, I'm going to simplify that, guys. How can I simplify this right here?
Cancel the 3.
2 factorial.
2 factorial, yeah, you got a 3 that's going to cancel out, and you're going to be left with a 2 factorial. That's exactly right. Now, that's sort of an application of what you were asking me the other day, Alexis. You got a 3, you got a 3, 2, 1. The 3s are going to go and leave you with a 2 times 1, so 2 factorial. What's going to happen in this one?
2 factorial.
It's going to be over
4
4 factorial, right? Because the 2 5s are going to drop out, and then you're going to have 4, 3, 2, 1. What's going to happen in this one?
6 factorial.
6 factorial in the bottom, right? So that'll be minus 6. If I bring down the 6, that'll be my x. Sorry, that'll be x to the 6. I've already differentiated it. And that'll be over 6 factorial. Now, interestingly, if I were writing a generic term for this one, I would notice that all the powers were what kind of numbers?
Even.
They're even, and so are the factorials underneath. So when I write that series representation, it's going to be equal the sum from 0 to infinity of, it looks like 2n factorial, so because the numbers are even. And by the way, guys, that's a 0 factorial if you want to think about it like that. And the x's are raised to the 2n factorial. I mean, not factorial, to the 2nth power. Sorry. What's in the bottom is the factorial. Check and see if it works. That's what the derivative looks like. If you let it equal 0, you'll get x to the 0 is 1 over 0 factorial. If you let n be 1, you'll get x squared over 2 factorial, and so on and so forth. So there's a series representation for cosine. All right, now, I'm going to cut down the homework somewhat here. The Maclaurin series are when you let C be 0. The Taylor series is exactly the same thing, except instead of 0 here, you end up with, you have C, all right? It's not 0, it's powers of like x minus 2 or whatever. I'll come back, I'll do that Monday, although I will point out that it works exactly the same way. It's not as easy though, because when you're trying to find the ANs, you're going to be plugging that C into the function instead of plugging 0 in. 0 is for Maclaurin specially. He did that, and then Taylor expanded on this and said, well, it works for any C. It doesn't necessarily work just for 0. Okay, so what I want you to, and I'll do that stuff. What I want you to see here, let me show you what the homework is. These 3 right here, these these, not that one. Those right there are Maclaurin series. These are finding series using known series. So for example, if I said, I want you to find x cosine x, you're just going to take the cosine series and shoot an x through it. And that'll give you x cosine x. If it says find, and then try this one. Now you hadn't done Taylor series. Don't do anything unless it has to do with Maclaurin series, okay? And that should be these. And 1, 3, and maybe 15 is really 15, is that? Yeah, 1, 3, and 15. Just those and those right there. I'll do Taylor series on Monday, and I'll be through with this, okay? Okay, get that quiz into me tomorrow sometime. I'll grade it, have it back before Monday. I probably am gonna put power series represent, you know what? I'm probably gonna jumble all this together. The next quiz, and it will most likely be the last quiz, I'm gonna put power series representations of functions on it, and along with Taylor series and Maclaurin series. So we'll just have one more quiz. And we've got a lot of quizzes, guys. I'm gonna drop some of your lowest quiz grades. Let me just real quickly, let me tell you how many quiz grades we've got. Just so you're kind of on top of everything right now. We got 14 quiz grades right now. I'm gonna drop at least 3. Okay. And that'll strengthen another.
You should have got your numbers before you came in.
What's that?
Nothing.
Who said that? Was that Tiara?
No, it was my aunt.
Oh, well, tell your aunt I'm going to drop 3 of your quiz grades, okay?
Okay,
Anyway.
she says she's going to drop 3 of our lowest quiz grades.
All right. Okay. Question anybody. We'll talk more about that next week when we get to the end stage here. And do what you can on that homework. Watch for an email for me on the other homework. You might want to start working on it. If I get it posted, I may not, but I'm going to post at the beginning of the week. We'll finish up Taylor series. And we're going to start something called polar coordinates on Monday, maybe Tuesday, definitely. Okay? Everybody good? Ready for another weekend? Inside or 6 feet away from everybody except your family? All right. Okay. I will talk to you guys later. Bye-bye. Have a good weekend.
Wait, hold on.
Hold on. Wait a minute. What?
I have a question.
Okay. What you got, Lexus?
About number 1 and number 4 on the quiz. I thought it was due today.
Okay.
So number 1, I'm pretty sure I messed up on it because like I was just juggling between like what the theorem says and like what I was trying to do like math wise. So I believe I simplified everything correctly. And then at the end I got like 3n over n plus 1. So I said like the limit goes to 3. So then I divided the 3.
Can you, I can't see you. Tell me.
I can join on my phone.
Well, I still probably can't see. Well, I could see you on the phone, couldn't I?
Yeah, because I'm using the laptop and that's
okay.
what messes me up.
How about doing that? And then read the problem to me before you go onto the phone. What was the problem again?
It was, I guess the
Sum.
The series. Yeah, the sum of n equals 1
Uh-huh.
to infinity, and it's like -3 to the n, x to the n plus 1,
Uh-huh.
then divided by n.
Uh-huh. Okay. All right. Get on your phone and let's talk about it.
Okay.
Okay, I got you. I can see you, okay? Can you see
Can you
my,
hear me?
yeah, I can hear you.
Mhm.
Can you see the board too?
Yeah.
Okay. Now, what we're trying to do on this, Alexis, is find the interval of convergence, right?
hmm
And what we do is we use the ratio test. So that you look at that thing and tell me what you're going to do first. Tell me what you did.
Well, the first thing I did was rewrite the -3 to the n. I
That's a good
rewrote it as
idea.
negative
That's a good idea.
1.
So I'm going to write it as -1 to the n, 3 to the n, x
Mhm.
to the n plus 1 over n. Is that what you did?
Yeah.
Okay, that's good. So what'd you do next?
I said like, well, -1 to the n plus 1
Good.
times, well, then I guess times 3 to the n plus 1
That's right.
times x to the n plus 2
That's good.
divided by n plus 1
All right, that's good. Then what?
divided by, oh, do you want me to just, the complex fraction, the -1 n
Yeah.
times 3 to the
Yeah,
n,
yeah, all
x
of
to the
that.
n plus 1 divided by n, and then
Yeah.
I cancel out the negative ones.
All right, let me write it first and let me let you look at it because I want to look
Okay.
at it and see. Okay, so that's 3 to the n, x to the n plus 1,
Mm-hmm.
and then over n plus 1. So it's exactly the same as what we had up there. So when I'm going to invert.
It's just over n.
Oh, it's just
There's,
over. Oh, you're
at the
right.
bottom,
It's
it's
just over
not
n.
n
You're
plus
right.
1. Yeah.
Yeah, it's right. You're right. You're right. It's just over n. So that's right. So I'm going to invert it and multiply. Okay. So I'm going to first of all note I'm not even going to waste my time with these powers of -1 because those powers of
Yeah.
-1 are going to go because they're in absolute value. Okay. So I don't have to worry about that. Now I'm going to invert and then I'm going to get you to tell me what you've got. All right. We're going to have 3 to the n plus 1, x to the n plus 2. When I invert, there'll be an n on top. Okay. When I invert, there'll still be the n plus 1 down there, and then this will be on the bottom. Is that what you got?
Yeah.
Yes? I hadn't simplified it yet.
Mm-hmm.
Okay, that's what you got. Okay, now talk to me about what you're going to do to simplify this thing.
So I rewrote like the power thingy so I could see what to cancel out. So I said 3 to the n times 3 to the first.
Good. So what cancels? We'll do it all at once. What cancels?
The 3 to the n's.
So that leaves me with a 3, doesn't it?
3.
Okay, so that's good. You're right there.
And then the x to the n's cancel, and then x squared divided by x is just x. So there's gonna be an x in the top.
Just an x to the first?
Yeah.
Okay, you're just subtracting this power down here. So the n subtracts and the 2 and the 1 subtract. So you're right, it's just x. What else you got?
And then there's the n over n plus 1.
Okay, that's right. Now, I like to kind of get this stuff out of there because it doesn't have anything to do with n's. So I'm going to write absolute value of 3x and then limit as n goes to infinity of n over n plus 1, which is what?
And 1.
Yep, that's going to 1. So we're left with the fact that we've got this absolute value of 3x, and what does it take for it to converge? It has to be what? What's the ratio test say?
I had to be less than 1.
Less than 1. So if I bring the 3 out, which I can because the absolute value of 3 is 3, and divide by 3, I'll have the absolute value of x is less than 1/3. Is that right? Is that what you got?
Yeah. That's what I got.
Good. That means that I think you're having trouble on the endpoints. What you're what this
Yeah.
means is that you've got x is between 1/3 and -1/3, right?
-1/3. Yes.
Okay. So my radius of convergence is 1/3. It's 1/3 on either side. Now I got to check the endpoints. Okay. Let's see what you did on that. Is that where you're having the problem?
Well, at first, like, I was just confused because, like, I didn't, like, I kept the 3 in there, if that makes sense. I didn't pull it out with the x. So then I got like, because the ends go to 1 and times 3 is 3. But I did the same type of math. I
That's
still got
fine.
1/3 to negative
That's fine.
1/3.
You can leave
I
the
just
in
think
there.
like checking.
Yeah. That's
Yeah, I
okay.
left it there.
Yeah, that's
And
okay.
then checking them, it got kind of bad because I started
Well,
rewriting
you know what?
things and it didn't help.
Here's the thing about checking them. Because they're 1/3, there's a power of 3 there, okay? Let's just put
Mhm.
one in and see how we can simplify it, okay?
Okay.
I'm gonna rewrite the series again. It was crap, I'm gonna go all the way back. It was -3 to the nth, x to the n plus 1, -3 to the nth, x to the n, x to the n plus 1. And what was it over? Tell me again.
And
Just n? Okay.
yeah.
Okay. So suppose I want to check 1/3.
Mhm.
And that's what, in other words, I'm going to plug in x equal 1/3 here. Okay.
Okay.
So let's look at what you got. That, I kind of like what you did about bringing the -1 and the 3 to the n out in the other thing. I would do it the same thing here, okay? I like that.
Mhm.
Then I got to put in the 1/3 to the n plus 1. And that's over n.
Mhm.
Okay. I have a feeling this is just a matter of not having enough experience simplifying it. But let me just ask you something. You got this power of 3 right here. You could actually rewrite that, because if you got a fraction raised to a power, it's the numerator to the power over the denominator to the power, right? And what's 1
Mhm.
to anything?
1.
1. So let's make
Mhm.
that change. So this is -1 to the nth. I forgot my n up there. 3 to the nth. That 1 to the n plus 1 is just 1. And then it's going to be 1 over 3 to the n plus 1. And then that's all over n. You see what I did?
So the numerator. Oh yeah, because the n plus 1 is just 1 in the numerator. Okay,
Yeah.
I
Yeah.
see.
All right, now, we're trying to simplify as much as we can here. Do you see anything else in here that you think you can simplify?
I can cancel out the 3 and
Yeah, and what would be left with?
just oh golly, I know this. Okay, 3 and 3, 1, 5, 1. There's the 3.
Just the 3.
Yeah.
So 3 to
Yeah.
1. Look, this thing right here is just 3 to the n times 3 to the 1, isn't it?
Yes.
Okay, so let's do that. All right, so I get sum -1 to the n. I think the 3 to the n will go with that 3 to the n and just leave me with a 1/3. And then it's over n. Okay. See how that worked?
Yeah.
If I want to, this is just a constant. If I want to, I just pull it out here and it might clarify your thought. Now, your job here is to tell me whether this thing converges or
Okay.
diverges. What you think? What kind of series is it?
That diverges.
Wait, what kind of series
It's
is it?
harmonic.
No, it's not. You know why it's not?
Oh,
harmonic?
it's alternating.
Yeah, look at it. It's alternating.
Golly.
Okay.
So
So,
I take the limit.
well, yes. The first thing, what are the 2 conditions for the alternating series test?
The limit and decrease, making sure it's
That's
decreasing.
right. So you look at this. How about the limit as n goes to infinity there?
That goes to 0.
Check. Now what do you got to do to show it's decreasing?
Take the derivative.
All right, so if I look at this as n to the -1, that's f of n. What's the derivative?
-1 and 10 -2.
Negative 1 n to the minus 2, which is just minus 1 over n squared, decreasing or not?
It's decreasing.
Yeah. 'cause
So
it's
that
negative.
does converge. Oh,
Okay.
golly.
Now, the only other thing you have to do is check the other
This
endpoint.
is just,
Okay?
yeah. That one, I really, I try to combine things. But I guess rewriting it in that way makes it easier.
Yeah, it does.
Because when I started saying like 1 to 2 and plus 1, I didn't know what to do with it.
Okay.
Like,
Always,
at all.
if you see
yeah.
something like this, break it down because you're going to be able to cancel part of it. And unless you do that, you can't see what's happening. You look at this one, you pull the 1/3 out, you're like, oh, that's easy. That's an alternating series. Okay. Now you got to check the other endpoint. The other endpoint is minus 1/3. Be careful with that one because it's got another minus in it. Something different might happen. Okay. But it's going to be
Yeah.
similar. It's going to be similar. Does that make sense?
And yeah, that makes more sense. And then I guess with number 4, like, because there was an x minus 1 instead of just like an x, I got all the way to like saying like it's gonna end up being 1/4 times the absolute value of x minus 1, and it has
So
to be
you got
less than
something
1.
like, yeah, you got something like this: 1/4 absolute value of x minus 1, right?
Yeah.
And that has to be less than 1 for this to converge, right? True?
Mhm.
Okay, so what do you do next?
I wasn't sure if I wasn't sure if I should distribute the 1/4 in there
No.
because
You're trying to isolate this because
Okay.
it's x minus 1s you're interested in. So what are you going to do with that 1/4? What do we do?
multiply
Yeah, what do we do back here?
by 4.
We multiply, yes, multiply by 4, exactly. So that's going to look like absolute value of x minus 1 less 4 is less than 4. Now, tell me what that says. This is all algebra. Tell me what that says.
Goes from 4 to -4.
Okay,
Well, of x minus 1.
right. Okay, now finish it up. Where's x?
At 5 and -3.
Yeah, and I'll tell you that I think you do have that one right. But now what do you got to check?
The endpoint.
You got to check the endpoints by plugging them in back into the original.
Okay. I think just earlier, because I was looking over the theorem again, and when I got that 3, like, for some odd reason, I was like, well, maybe it diverges because it's greater than 1. Or, like, it's, like, greater than I forgot, but then I was just like, I don't know, because, like, if I divide by 3, then it'll be less than it.
If you simplify it right, a lot of those things are going to drop out and maybe leave you with a constant, and you can pull a constant in or out. It's not going to make a difference to the convergence of the series.
Okay. Because I remember I was just like, the first time I did it, I got something that didn't make sense. And I was just like, okay, well, that's because I'm not taking my time on it. I think I rushed and I messed up canceling things out because I didn't add the 1 to the x plus, like when it was like already like n plus 1 plus 1.
Yeah.
I just kept canceling it out, but I had to remember to add it.
Yeah.
Okay.
Yeah.
This wasn't as bad as I thought.
Yeah. No, it's not. And I just have to spend a little time. Actually, it takes more time. Well, aside from the simplification, it takes more time to check the endpoints than it does to get your interval, usually, you know. So you got to look at those. And be careful. You're looking at them, look at it and say, is it an alternating series? Is it not an alternating series? If, for instance, if that one up that we had before, if it had looked like that with the 1/3 outside and it had not been alternating, what would you have said about that?
It diverges.
Because that's the harmonic series times a constant, right? So that's going to diverge.
So anytime there's like a -1 to an n, that's just alternating.
If it's alternating, well, if it's -1 to the n, it's alternating. We've seen series that can go minus, minus, plus, plus, minus, minus, plus, plus. So you got to be careful with that. But if it's -1 to the n, it's going to alternate. Because 1, 2, 3, 4, you're gonna get a plus one time in the next note, and so forth and so on. Okay. Make sense?
Yeah, it makes sense.
Okay. All right. Well,
Alrighty.
Watch the video again from yesterday after what I said today, just to kind of imprint it in your mind about what we're doing with those things. That'll be the next homework assignment that we look at. Actually, yeah, it'll be the next one we look at.
And I did that homework about I guess like if things are centered at a different spot.
Yes, yeah.
And the way I did my partial fractions,
Hmm.
I think I ended up getting the same thing y'all got. I just put them over I just said A was over a different fraction.
Okay, well, yeah, well, it should be careful. I mean, you might have called A and B something different than we did. You might,
Yeah.
if you had factored it into x minus 1, x plus 3, and I did x plus 3, x minus 1, your A and B would be different, but it would come over the same fraction in the end.
Because I was just at first I was trying to follow, but I was like, oh, we put them over two
Yeah.
different things.
Yeah.
But that wasn't bad.
Okay.
I was just worried about the last one. Was the last one supposed to be a partial fraction question because it was x squared?
No. Let me look back at the example. Look at this. If you had, it still looks like a geometric series. If something, I don't remember what it was, but if it had been 2 plus x squared or something,
Mm-hmm.
then I could have written it as 1 over, first of all, I would have divided everything by 2.
Mm-hmm.
Okay. And that would have been x squared over 2. And that would have been 1/2 over 1 minus that. Your R is just x squared over 2. Oh, you could have done that with partial fractions. Because if it had been 1 minus x squared, you could have factored it, right?
Mm-hmm.
Was that 1 minus x squared or was it 1 plus x squared? I don't
It
have
was 1 minus x squared.
you could have done it in partial fractions, but you don't have to. Because you could say,
Okay.
well, R is x squared. So that means the absolute value of x squared has to be less than 1. And then if x squared is less than 1, then x is less than 1. So you could have done it like that. So there's your R, your A is 1, and you can form your series then. So as long as it's A over 1 minus some R, but this one you could do by partial fraction. You're absolutely right. Okay.
Mm-hmm.
I might have done it by partial fractions. I can't remember. But anyway, yeah. Look at my key. The key's online, okay? I don't know. The keys, I put it online right before class. So look at that and see what I did. I can't remember what I did. Okay? Could have done it one of 2 ways.
Alrighty.
You okay?
Yeah, I think I'm better about this stuff.
Okay, spend a little time on them
Yeah.
over the weekend and look at my keys and so forth, and I think it'll sort of start to make sense, okay?
Okay.
All right.
Alrighty. Have a good day.
All right. I hope your neck's better. I hope
it gets better too.
I was thinking it was because you have to sit at the computer all day long. That's bothering my back. I don't know about my neck, but it's bothering my back. So anyway, whatever.
I don't know what happened. Yeah. Alrighty. Have a good day.
All right. I'll talk to you later. Bye.